All right, so we ended in our last video with the combined gas law. And so what I want to do now is we're going to work through some of the examples that are in your notes. And I'm actually going to do the even numbered examples with you. So let's move to example number 2. This is in your note pack that each of you should have. Example number 2. And let's talk about how you should always show your work. This is what I would expect for you to show as you work through these problems. Always label your givens, identify your givens, show your formula, plug into the formula, and then of course round your answers to proper sig figs and include your units. So let's look at number 2. A balloon contains 43.1 liters of helium gas at 1.00 atmospheres of pressure. What will the pressure be if the volume increases to 63.9 liters? So let's identify our givens. The first number we see there is 43.1 liters. So this is volume, so we're going to call this V1. You can tell from the context clues that the gas is at 1 atmosphere of pressure, so that P1 is going to be matched up with the V1. So we're going to label that as 1.00 atmospheres. Next says what will the pressure be? So you're looking for a new pressure. So P2 is what we're going to call that. Since P1 is in atmospheres, P2 will end up being in atmospheres as well. Always pay close attention to your units, guys and gals. All right, so for the last number here, 63.9 liters. So that's the volume. We're going to call that V2. So 63.9 liters. Now, always have the combined formula for reference. If you look at your combined formula, remember that's P1 times V1 over T1 equals P2 times V2 over T2. If you learn this formula, you can derive the other formulas from it. So have this kind of to refer to, so that will help you in figuring out what formula to use for this problem. Notice as you examine your variables, you only see P's and V's, so that means the temperature is constant. So if you drop out the temperature in this formula, your formula that we're going to use is P1 times V1 equals P2 times V2. So this is our formula. Another thing you want to check for is make sure your units agree. Liters and liters match, so that's good. Atmospheres and atmospheres match. So all of our units are in agreement. We're solving for P2. So I'm just going to plug into my formula. So we're going to go right straight down our givens and we're going to plug in. P1 is 1.00 atmospheres. V1 was 43.1 liters. P2 is what you're looking for, so I'm going to leave that as P2. And V2 was 63.9 liters. So now we need to isolate our variable here, so we need to divide both sides by 63.9. So divide by 63.9 liters and divide by 63.9 liters. This is going to let your liters cancel, and it will isolate your P2, which is what you want. Notice here the units, liters, cancel with liters. And you need 3 sig figs because all of these are tied with 3. So for our answer here, we're going to round that to 0.674, and the unit is atmospheres. Make sure you always box in your final answer, round it to proper sig figs, and include your units. All right, let's look at example 4. Here it says you have a 5-liter sample, so 5.00 liters, and that's the volume. We'll call that V1. And it's at 20 degrees Celsius, so that's the temperature. That's going to be labeled T1, 20 degrees Celsius. Now remember, all of our gas laws, when you plug into the formulas, you have to plug in your temperatures in Kelvin. That's an always kind of thing. So we're going to need to convert this. Let's add 273. This will give us 293 Kelvin. Keep on reading, and it says that it's heated at constant pressure until it reaches a volume of 8 liters, so 8.00 liters. Then it says, to what Kelvin temperature must this be? So we're looking for T2, and of course, since we plug it in Kelvin, it's going to end up in Kelvin, and they did ask for the unit to be in Kelvin, so everything's going to be good with that. The volume units match, the temperature units are in Kelvin. Now we need to figure out what formula to write down. So refer back to your combined formula, and you will see that we're dropping out the pressure. So your formula that you're going to plug into is V1 divided by T1 equals V2 divided by T2. So let's plug into this. V1 is 5.00 liters. T1 is 293 Kelvin. V2 is 8.00 liters, and you're looking for T2. Now be careful with this one because since our variable that we're solving for is in the denominator, you're going to need to make sure that you isolate the variable and make sure it's in the numerator. So we're going to have to cross multiply here to isolate our variable. If you rearrange this and isolate the T2, then you're going to end up with plugging in this into your calculator this way. So if you get your T2 in the numerator, you have to bring it up. We're going to leave the 8.00 right where it is. 8.00 liters stays where it is. We need to bring the 293 up. So 293 Kelvin will come up to the numerator as you cross it up. We crossed the T2 up already. I put it here. So you need to bring the 5.00 down. I'm just rearranging this, isolating the variable. This is just algebra, y'all. So you do it the way that you feel comfortable. All I did was get my T2 in the numerator and I'm isolating it. Notice the liters cancel with liters. We have 3 sig figs all the way around here. This is going to leave you with your temperature. And the temperature in Kelvin is going to be 469 Kelvin. That's the 3 sig figs. Okay, let's look at number 6. Number 6 says, before a trip from New York to Boston, the pressure in an automobile tire is 1.8 atmospheres. And that's the P1. And they tell me that was at 20 degrees Celsius. So that's going to be my T1. At the end of the trip, the pressure gauge reads 1.9 atmospheres because as you're traveling, there's going to be friction. So it's going to increase the temperature, therefore increase your pressure. So it wants to know what is the new Celsius temperature in the tire. Now notice it does say what's the new Celsius temperature. So we know that when we plug in, we're going to end up with our temperature in Kelvin. So this is just a reminder that when you get done, you got to convert it back to Celsius. Remember here at 273, that's going to give you 293 Kelvin here. And we have both of our pressures in atmospheres. So we're going to plug in. Now the formula that we need here, because the volume is constant, is P1 divided by T1 equals P2 divided by T2. And this is what we know is a Gay-Lussac's law. P1 is 1.8 atmospheres. T1 is 293 Kelvin. P2 is 1.9 atmospheres. And T2 is your X. We're going to isolate the variable again. So when you isolate your T2, and I don't have a lot of room here, so I'm going to let y'all do the algebra on that. But when you isolate your variable on that one, you're going to end up getting for your T2, it's going to round to 310 Kelvin. Now remember, this is in Kelvin, and they did ask for it in Celsius. So to get back to Celsius, we need to subtract 273. And this will convert it back to Celsius. So you're going to end up getting, for your answer, 37 degrees Celsius. That will be your final answer. Okay, last example, we'll go straight to number 8. This is a sample of gas occupies 2.30 liters, so that's a volume, at 825 millimeters of mercury. That's going to be a pressure. At 70 degrees Celsius, so that's the temperature. Add 273 to that because you got to convert it, and that's going to give you 343 Kelvin. Then it says, what is the volume? Question mark. Since our V1 is in liters, V2 is going to be in liters at STP. Now, you might think they haven't given you enough information, but remember, STP is a defined quantity. It's a specific set of conditions. So standard temperature is 0 degrees Celsius, which is 273 Kelvin, and standard pressure is always 1.00 atmospheres. Now, since they're part of a definition, they do have unlimited sig figs. Remember that. This is going to be the combined gas law. P1 times V1 over T1 equals P2 times V2 over T2, because only the quantity of gas is constant, but the other variables are all changing. So P1, 825 millimeters of mercury. Now, pay attention to your units, y'all. Do your pressure units match? This is in millimeters of mercury. This is in atmospheres. They do not match. So we need to convert so they both match. I'm going to choose to convert this one down here, atmospheres, to millimeters of mercury. So remember, 1 atmosphere equals 760 millimeters of mercury. So you got to show your work for all your conversions, and this is going to give me 760 millimeters of mercury. So you're going to plug